Hello everyone, and welcome back to another video where we are going to be complex analysising an awesome Maths 505 integral. You know it's going to be awesome because it's one of Maths 505's integrals. And it's complex analysis. Those two things together just make for an awesome video, I think. But anyway, without any further ado, let's just get started. The integral we're going to be using, the contour we're going, the integral's right here, yeah. The contour we're going to be using today is just the keyhole contour. So it's going to be this one right here, where we're integrating twice over the positive real axis, one from left to right, right here, and one from right to left as such, and then also around the origin and around the whole plane itself, connecting the two parts of the contour right here that are on the positive real axis. So actually naming all of these terms right here, all the parts of our contour, we're going to have gamma 1, gamma 2, gamma 3, and then gamma 4. And the interesting part with these integrals with natural log in them is that what we're going to do to actually evaluate it is raise the power of the natural log, and the function will be finding the residues of and integrating over this contour, which might seem a bit counterintuitive, but let me just kind of show you why that might actually make sense. And the answer is going to lie in, well, the following. So our integral over our entire contour is going to be equal to the sum over the integrals of each individual part of it. So this is going to be the integral over, say, gamma 1 plus the integral over gamma 2 plus the integral over gamma 3 and then plus the integral over gamma 4. And the integrals over gamma 1 and gamma 4 aren't too interesting, right? Because they're just going, I'll say straight up, they're just going to go to 0. And the reason for this is effectively as follows. The substitution that we would make here is x equals re to the theta I. And what this would turn our integral actually into would be the integral from 0 to 2 pi of I re to the theta I. That comes from just finding d theta. So d theta is out here. Well, natural log, but then to the third of r e to theta I. I promise I will explain why it's to the third in a second. And then we have a 1 plus r squared e to the 2 theta I, and then divided by 1 plus e, or really r to the 4 e to the 4 theta I. And I'm not going to prove it extremely rigorously here, but you can really see that if we take the limit as r goes to infinity, the limit here is just going to be 0, because at the end of the day we have an r to the 4 term that's just going to dominate the entire limit and make the whole thing go to 0. And similarly, what we have whenever we let r go to 0 is that, well, in these terms right here, so in the ones with the 1 plus, that right there is just going to give us like a 1 over 1 effectively, leaving us just with the terms of r, but then also natural log to the third of r. And this gives us, something like this. So r natural log to the third of r, something along the lines of that. And the limit as r approaches 0, and this right here is just going to be 0. I will leave it to you to prove, but effectively that's why both of those integrals right there are 0, because the radii are going, one's closing in on the origin and the other one's like going out to infinity, so the limit of both those is 0. And what this leaves us with is something quite interesting. We have the integral over gamma 2 and also the integral over gamma 3. So what's the integral over gamma 2? Well, quite plainly, it's just the integral from 0 to infinity of natural log to the third of x times 1 plus x squared, and then all over 1 plus x to the 4 dx. That right there is the integral over gamma 2. Which begs the question, how on earth are we supposed to get a natural log squared out of this? And the answer in that lies in the integral of gamma 3. If we were to take this natural log term at face value, these integrals would just cancel, but that would not be helpful for us at all, because we would just get 0, and we don't want that. So instead, what we can actually define this natural log to be is the following. And this is based on really the following properties as well. If I have some e to, e to the xi, right? Some complex exponential. But then I go ahead, because I'm feeling like it, I go ahead and I just add 2 pi I to it, right? The answer, well, what is that going to give me? Well, the answer is just, it's going to give me e to the xi. because e to the 2 pi I is just 1. So if we let, this be some complex number, what we can see is that the natural log of z is equal to, xi, but then also 2 pi I. And what this is really reflective of is the following definition of the natural log in the complex plane. You can define natural log in the complex plane to be, well, the natural log of z, or the natural log of the absolute value of z, but then plus I times the argument of z. And that's one way you can define the complex natural log function. So on our primary axis, on gamma 2, the argument to z we can just say is 0 because we're going from left to right. But whenever we're integrating over gamma 3, because we've already gone around the circle once, we can think of it as the argument of z not just being 0, but instead this 2 pi I. So one way we can write this natural log term in the integral over gamma 3 is actually as natural log of x plus 2 pi I all to the third. And then we have, our integral from infinity to 0, of course, over 1 plus x to the fourth, and then times 1 plus x squared dx. But let's evaluate this natural log of x plus 2 pi I all to the third real fast. This part is extremely important. So by the binomial theorem, or if you just kind of remember the third-ish line of Pascal's triangle, 1, 3, 3, 1, we can remember that this right here is just natural log of x to the third, and then plus, natural log, plus 3, natural log squared of x times 2 pi I, and then plus 3 times the natural log of x times 2 pi I squared, but that's just going to be 4 pi squared, but with a negative, because I squared is -1. And then we have 2 pi I to the third, which is just going to be minus 8 pi cubed times I. So that right there is quite daunting to begin with, but I do promise it does simplify. And then we're going to have a plus x to the 4 right here, and then r1 plus x squared. But, that's a pretty big but right here. Our integral over gamma 2 was what? Kind of the same thing, but just with a natural log to the third in it. The integral here, so I'll just write it out, from 0 to infinity, but we have the integral over here is the integral from 0 to infinity, but it has a negative in front of it. So let's just compare real fast what exactly is going to cancel here. And the answer is that the integral over gamma 2 is going to cancel with part of the integral over gamma 3, because you'll see here that, we have a natural log to the third, and a minus sign right there. So those are going to cancel. And if we look really closely inside this integral, what do we kind of see lurking in there? Well, the answer is, the integral we actually want, the natural log squared integral. We can see that right about here. So, kind of simplifying this a little bit, we have minus 6 pi I times big I, our integral, plus 12 pi squared times integral 0 to infinity, natural log of x, and then over 1 plus x to the 4, and then 1 plus x squared dx, and then plus 8 pi cubed times I, and then times this integral right here, the integral from 0 to infinity of 1 plus x squared over 1 plus x to the 4 dx. That right there is the simplified version of the integral over our entire contour. But you'll see a couple of interesting things here. Namely that, this part right here, that right there is going to be just a real number. To which you might say, and? But the super important part about that is that we know that our integral that we want and ultimately want to solve for, that's going to be some real value. So if we were to, say, isolate our integral right here. So divide everything by negative 6 pi I. So I, plus, I'm going to call this whole quantity q, honestly, because that's not too important. So q over, minus 6 pi I. And then plus this right here, so minus 8 pi cubed over I, and then 6 pi I. You'll see that the i's here actually cancel. Then times the integral from 0 to infinity of 1 plus x squared over 1 plus x to the 4 dx. Well, you see here that we have a real value right here and also something real right here, but this right here is imaginary. So if we just take the real part of everything, then we can just eliminate this quantity, and we just, quite frankly, don't have to deal with it. So let's go on to kind of the second half of what the residue theorem tells us, right? And what does the integral over our entire contour actually equal? Or I suppose that is the main part of the residue theorem. But just as a reminder, the integral over all this is also going to be equal to 2 pi I times the sum of all of our residues. 2 pi I times the sum of all of our residues. All of this is equal to that, so whenever we divide it by 6 pi I, come back here, this is equal to 6 pi I, or sorry, 2 pi I times the sum of our residues. We're also dividing by 6 pi I, right? So this right here is equal to 2 pi I over 6 pi I, which is just a third times the sum of all of our residues. I just want to make that clear before we go any further. So now our integral has been divided into two parts. The first one has been this integral right here, where we have a 1 plus x squared over 1 plus x to the 4. And on the right hand side of the equation, we have a 1/3 times the sum of all of our residues. So to actually evaluate I, and again, I should say this, we are taking the real part of all this right here. The reason I didn't write it is because it does actually turn out that all of our residues are real, but I'm jumping ahead. So for now, let's focus on this integral right here. I say this integral, there's like a bunch of them, but this one right here that I'm zooming in on, this 1 plus x squared plus 1 plus x squared over 1 plus x to the 4. What on earth is that? So let's investigate. What is this? And the way we're going to evaluate this, we can do it a couple ways, but seeing we're already doing a bunch of complex analysis, a little bit more can't hurt, So just taking this right here, I'm going to call this I2 real fast. So I2, what we can say is that 2I2 is equal to the integral over all real numbers of 1 plus x squared over 1 plus x to the 4 dx. And we can just use the residue theorem here, actually. Or sorry, we can use complex analysis here just to determine what this integral actually is. And let's just do that, shall we? So we're just going to be using this contour right here. And we're going to have two poles right here, because we're going to have poles at e to the pi over 4, or pi I over 4, and then also e to the 3 pi I over 4. Those are the only ones that are actually going to be enclosed by our contour. There are others that we're actually going to be dealing with later, but for now, let's only worry about these. So by the residue theorem, our whole line integral is going to be equal to 2 pi I times the sum of our residues. So we have 2 pi I times, our residues. So what's the residue at e to the pi I over 4? Well, if we have, like x minus pi I over 4, and then times 1 plus x squared over 1 plus x to the 4, what we get is a 0 over 0, because we're taking the limit as x goes to 0. So we can just use L'Hopital's rule to kind of make everything just a little bit easier, so that way we don't have to factor out a bunch of stuff in the denominator, because quite frankly, that's a little bit nasty. So using L'Hopital's rule, what we actually find is that, well, we need to differentiate this term for it to not go to 0. So we have an x squared, we're taking the limit as x approaches e to the pi I over 4, pardon me. But in the denominator, whenever we differentiate, we're going to have 4 and then x cubed. So whenever we plug in x equals e to the pi I over 4, what we end up getting is e to the 3 pi I over 4, and then times e to the pi I over 2. And then similarly, what we have is more or less the same thing. with e to the 3 pi I over 4. It's in the same structure, just we're going to replace where we put e to the pi I over 4 in the previous one, we're just going to put e to the 3 pi I over 4. So we have e to the 3 pi I over 2 plus 1, and then divided by 4 times e to the 9 pi I over 4. So let's go ahead and just simplify all of this real fast, shall we? E to the pi I over 2, what's that? That's just going to be I. So we have an I plus 1. I'm gonna factor out a 1/4 right here, so it's a pi I over 2 times all this. So pi over 2, and then what is e to the 3 pi I over 4? Well, one way we can think about that is the following. If we have, just in the complex plane, it's going to be around here. But if we multiply that by the square root of 2, square root of 2, then square root of 2, what this point actually becomes, this right here at least, is just going to be minus 1 plus I. You can verify this for yourself, because you see that the magnitude in this case, with the addition of a square root of 2, is just going to be, the magnitude of this point right here is just going to be the square root of 2, so that's why we add the square root of 2 there. And then you can also see that it is at a 45-degree angle with the imaginary axis, and then you add the extra 90 due to this right here, and then what you end up getting is a 135-degree angle, or 3 pi over 4. So what this denominator actually is we have a square root of 2 out front, but then we have a minus 1 plus I right here. And similarly for this right here, 3 pi over 2, well, that right there is just a minus I, so minus I plus 1, and then divided by, what is e to the 9 pi I over 4? We know that 9 pi I over 4 you can simplify to just 2 pi I plus pi I over 4, but e to the 2 pi I is just 1, so this right here is just an e to the pi I over 4. And we know that e to the pi I over 4 is just 1 plus I over the square root of 2. So similar to the last one, we're just going to have this extra factor of the square root of 2 out front. And then 1 plus I. And multiplying the top and bottom of each of these by its appropriate complex conjugate. So for this one right here, we're going to multiply by 1 plus I. And then we're going to be multiplying this one right here by 1 minus I. So what we end up getting is 1 plus I, or I plus 1 squared, divided by I minus 1, I plus 1. And, the bottom is just going to be negative 2. And over here we have, something very similar. We have 1 plus I, and then 1 minus I. And the denominator here is just going to be 2. So erasing that, we have just 2. But then the numerator is going to be I'll write this 1 minus I squared. And let's evaluate these numerators real fast. We have I squared, which is negative 1, plus 1 squared, which is 1, which is 0. So the only thing that survives is the 2ab term in the squared formula. So what we have is 2I times 1, really for both of these. So we have 2I, but then we have a negative I here, so we're going to have negative 2I here. And you'll see the following. The 2's cancel. Woohoo! But then we also have, both negative i's. So this right here is just going to be negative I times the square root of 2. And bringing this term down right here, what we find is that this in total is just going to be pi I, there's an extra 2 here, pi I times the square root of 2, and then times negative I. But the negative I and negative I are just going to cancel. So what we end up getting for this in total is just going to be pi times the square root of 2. So that right there was a fun little treat in and of itself, but let's see how this relates to the integral as a whole. So we found this right here is pi times the square root of 2. So then I2 we conclude is just going to be, pi over the square root of 2. Or since it's probably better to keep everything in the all radicals in the numerator, we can say this is pi times the square root of 2 over 2. So given that, and also our coefficient up front, which we might as well simplify to 4 pi squared over 3. What we find is that, let's simplify all of this actually. We find that our total I right here is equal to pi root 2 over 2 times 4/3 pi squared, and then plus 1/3 times the real part of our residues, or rather the sum of our residues. So we can simplify this right here actually just real fast. So we can say this is a 2, 1, and then a 2, and then that's just going to be pi to the third. So really it's a 2/3 pi to the third root 2. So now this is just a matter of finding the sum of all of our residues. So let's go do that, shall we? I'm going to write our function out right here on top. So our actual function we're going to be using for this is going to be this natural log to the third one, because that's the function we're actually integrating over with the contour, integrating the contour over with, however you might phrase that. Natural log to the third of x times 1 plus x squared, and then divided by 1 plus x to the fourth. And what are all of our poles going to be here? Well, we know we're going to have poles whenever x equals e to, I'm writing theta in general. No, we want specific values, don't we? Pi I over 4, pi e to the 3 pi I over 4, e to the 5 pi I over 4, and then finally e to the 7 pi I over 4. And the cool thing is that you're actually, if you were to look at these graphically, what these would look like on the complex plane, I'm drawing the circle, well, you'll see why, they would just fall like this. 4 corners of a circle like this, each a 45-degree angle from any given axis, which is really cool. But anyway, our first one is going to be, well, let's just start with e to the pi I over 4, right? So now we have natural log of e to the pi I over 4 to the third, but wait, real fast, let's just think about this. That's just going to be pi I over 4 to the third, because, I mean, there's just an e in there. So it seems rather silly to leave it as that. So I'm just going to write some of our residues right here. What we're going to have is pi I over 4 to the third. And then what are we going to have? Well, I'm just going to write this in general right here. So that way I don't have to do this a bunch of times separately. So if x is a pole of, this right here, if x is a pole of f, then what we can say is that, if it's at if the pole is at k, then this right here, so we have natural log to the third x, because this is just the formula for a residue. All of our poles are simple poles, so we can just do this right here. If x is the pole of f at point k, then the limit of this, so the limit as x approaches k, of this right here, well, we can just straight up evaluate that using the L'Hopital's rule. And the derivative of the numerator, that is just going to go to 0 for every single term where this is not differentiated. So we're just going to differentiate that term, which just gives us 1, are going to be left with natural log to the third of, well, k, and then 1 plus k squared. And then the denominator, we're going to have a 4 times x to the third, or really a k to the third. So given that this is the case, instead of going and evaluating every single residue with the limit, we can just kind of use this general formula right here. That right there is going to stand the pi I over 4 to the third. But what we're going to have is an additional 1 plus k squared, but k squared in this case is going to be e to the pi I over 4. So we're going to have 1 plus e to the pi I over 2, because that's squared, and then divided by 1 plus, 4, and then e to the 3 pi I over 4. And then similarly, we're going to have plus. Our next term right here is going to be e to the 3 pi I over 4. but with a natural log term, that's going to be 3 pi I over 4 all cubed. So we're going to have 3 pi I over 4 all to the third power, and then times 1 plus e to the 3 pi I over 2. I mixed up the order, but that's okay. Divided by 4, then times e to the 9 pi I over 2. And then we're going to have plus, it ends eventually, I swear, plus, let me keep that on screen, plus, well, 5 pi I over 4 all cubed. And then we're going to have our 1 plus e to the 5 pi I over 2 divided by 4 times e to, well, it's 3 times 5, well, it's going to be 15 pi I over 4. And then one more time, plus, this is the one downside to complex analysis, it does get a little bit messy at times, plus 7 pi I over 4 all cubed, and then times 1 plus e to the 7 pi I over 4 divided by 4e to the 21 pi I over 4. Or pardon me, that should be a 2. Whoopsies. Okay. Boop. Oh no, the parentheses don't match color. No. Okay. And that right there is the sum of our residues. So I hope you enjoy it. No, I'm kidding. We're actually going to be evaluating this. So let's just go ahead and take a look at all this. So we've already evaluated some of this, actually. So there's 1 plus e to the pi I over 2 over e to the 3 pi I over 4. Well, if we just kind of scoot on over here, we've already evaluated this to be, we scroll down here, we've already evaluated this term specifically just to be minus I square root 2. This 2 right here comes from the fact that we're just adding them twice, right? So what this right here is just square root of 2 minus square root of 2 times I. So using that right there, for both of these, in fact, we can simplify a great deal of our work. So this right here is just minus square root of 2i, and this right here is also just minus square root of 2 times I. So then, the question becomes, what are these right here? What are these chonkers? Well, that pie is missing a leg. My goodness. It's like a pirate pie. Oh, it's a pirate. Ah, there we go. Wouldn't be a ginger math video without some amazing top quality puns. So e to the 5 pi I over 2. What exactly is that? Well, 5 pi over 2, that's just 2.5. But e to the 2 pi I is just 1, so that right there is just going to be I itself. That right there is just I. And similarly, e to the 7 pi I over 2, that's just going to be, you can think of that as like half a pi less than e to the 8 pi over 2, which is just like 1, so you just multiply that by negative I and end up where it's supposed to be. So that right there is just negative I. If you think of I as like a rotation in a way. So let's deal with the denominators real fast. So e to the 15 pi I over 4, we can think of that as 1/4 less than, or pi I over 4 less than e to, like, you know, the 4 pi, or 16 pi I over 4, which is e to the 4 pi I, which is just 1, right? So we can think of that, again, as a sort of rotation. So we're here, and we just go like minus pi I over 4 that way. So what that is just minus I, or sorry, not minus, plus I, or it is minus I, so 1 minus I, pardon me, over the square root of 2. And similarly, this right here, this e to the 21 pi I over 4, we can think of as being 5 pi I over 4 more than 1. So this right here would be the same thing as like e to the pi I over 4, which is just going to be negative 1 minus I over the square root of 2. So simplifying all these terms right here, we find that we have 5 pi I over 4 to the third, and then 1 plus I, 1 plus I over 1 minus I. And then here we have minus 1 minus I, and then we have a 1 minus I here. And we have a square root of 2 outside of all this as well, so square root of 2, square root of 2, I'll add the plus. And then just slowly filling in all of our terms, we have a 7 pi I over 4 also to the third. Okay, this right here is what we have, but this looks awfully similar, doesn't it, to things we've had previously, because we have a 1 plus I over a 1 minus I. But what exactly did we have before? Scrolling over. Earlier we had a 1 plus I over negative 1 plus I. So comparing what we had, so earlier what we had was an 1 plus I over minus 1 plus I. But we can just clearly see that one is just the negative of the other because of the difference in the denominator. So instead of having to do complex conjugate stuff, we can just say straight up that this right here is just going to be I. And similarly, right here, to multiplying top and bottom by a negative, we see that this right here is going to be effectively the same thing, because this is 1 over our negative I from earlier, but we also know that 1 over negative I is just I itself. So this right here is also just going to be I. So we have simplified a lot of these terms. So let's write this out in one big simplified term, shall we? First thing I'm going to do is actually factor out a pi I over 4 cubed, because that's just a common factor in all of this. So scrolling or zooming in, we say this is pi I over 4 to the third. But then also notice that in every single one of these we had a square root of 2 over 4. A square root of 2 over 4 as well. So just going term by term at this point, we see that we have, well, here we just have a minus I. Here we have a 3 to plus 3 to the third times minus I. And what do we have here? Next we have a 5 to the third times I. And then we have plus a 7 to the third times I. And this right here is very much simplified and maybe even nice to look at. So evaluating a little bit more here, or simplifying a little bit more, we have the square root of 2 times pi cubed over 4 to the 4. But then I to the third is just going to be negative I. So we have minus I. And then I'm also going to factor out an I from all of this right here. So what we have is, I, but that right there is just 1. So what we're left with is minus 1 minus 3 to the third. But 3 to the third is just 27. Plus 5 to the third, which is just 125. And then plus 7 to the third, 7 cubed, which is just 343. Adding all these up, what we end up with is 440. Thank goodness for calculators. You gotta love them. But anyway, what we see is that we have square root of 2 times pi to the third and to 440 over 4 to the 4, which is actually just 256. But also remember that this is the sum of our residues. And what we needed to find was 1/3 of the real part of the sum of our residues. So let's find that real fast. So multiplying this by 1/3. But also just note, I think I said this earlier, but the real part of this is just itself because, well, it is only real. So putting this kind of ugly fraction in lowest terms, what we actually find is that this right here is 55 over 96 times the square root of 2 times pi to the third. But we aren't done, are we? That right there is the sum, 1/3 times the sum of our residues. But we also have this right here. So let's go ahead and actually compute this. And I do sincerely apologize. This right here should be a minus sign because we divided by negative pi I, or negative 6 pi I earlier. I simply forgot the negative. I do apologize. That does change things, I mean, not an awful lot, but we have 2/3. It gives us the right answer at least. So we have 2/3 times square root of 2 and then minus 55 over 96 times pi to the third square root of 2. And I will be completely honest, I'm going to just use a calculator for this part because those fractions are completely nasty. But what we end up with at the end of the day is a 3 pi cubed times the square root of 2 all divided by 32, which is indeed our answer to this awesome integral. So this was a longer video than normal, but I hope you all enjoyed, and I will see you all in the next one. Another shout out to Maths 505. Bye!